Assalamualaikum and good day everyone. So I just want to let you guys know that I will not speak with a high volume, okay, with loud voice, because it's already 12:30 a.m. and my housemates, they are sleeping, okay, so I don't want to disturb them. So hopefully this video my voice is still clear for you guys. If not, please increase your speaker volume, okay, sorry for that. So okay, so now we still in the week 5, which is about the electrostatic field in a medium. So previously we have covered about this, okay, conduction current density, IDQdt, IJDS, and then your in static condition the electric field inside is 0, and you have the rho v changed to rho s, okay, and then you also know how to calculate the current, okay, in many ways, IJDS, IDQdt, this one, okay, you guys can refer to the previous lecture, and also how you calculate the resistance based on the field theory approach. You have this R equals this, and you also have this option. And after that, how we come to derive these equations due to this condition, which is the conductor under static condition. So there we go for we come across this, right? So we have applied field, we have initially we have rho v naught, and we have the conductor with conductivity. When we apply field, then it will the rho v will change into rho s, okay, but at the time 0 it is rho v naught. That's why we have here rho v naught, okay, and this is the equations. So without further ado, we will I will try to make it into 2 equal page, so that we can see the comparison very easily, okay. Now we will go to the next part, which is the conductor free space boundary condition, okay. Okay, so let's say if we have a boundary condition. What is boundary? Is that boundary is when we have two different mediums, okay, of different characteristics. So I think you guys also learned during your physics, right? Okay, let's say we have a boundary, okay, let's say we have a boundary, and then we have let's say we name this as a medium 2 and this as a medium 1, okay, and we imagine that this conductor is our medium 2 and our free space is our medium 1, okay. So if there is a different material involved, means the characteristic of each material is different, then what if we put some electromagnetic signal passing through, it will be diverted, okay, it will be diverted, it won't be straight like this, okay. We can imagine as light passing through, okay, light passing through from the conductor to the free space, okay. So for example, if let's say if we have a line here, we take the line as normal, okay, and we have some electromagnetic wave, okay, we can imagine as a light, okay, because light is also electromagnetic wave. So it won't be same as straight, okay, because it will experience change in direction and also maybe in speed, maybe, okay, because it's different. We have, if you learn from in your physics, is we have index of refraction, right? Okay, so this one is one of the things that to easily relate with you guys. So let's say if we have like this, and the initial one, then we will see that it will go to this, okay. So you can see it is different, it won't be straight, okay, because when it's passing through this boundary, it will have some change in direction and maybe in speed also, okay. So then here is your E1N. Okay, so you have your E1 and you have your E2. So this is initial your E2 and this is initial of your E1. Okay, it is a vector because it have scalar and also it have direction. Okay, now to simplify the calculations, okay, we need to have some understanding, so we need to have some solution so that this one can be settled easily. Okay, because if you see in these situations, okay, if we don't try to solve it in different way, we will have E2 at different direction, at different angle, and in different angle with this. Okay, they will have their own angle, and also it's difficult to solve it, so we need to settle it, solve it in simpler way, in such a way that it can be represented in things that cannot and will in a thing that is similar with the boundary. Okay, for example, whether it can be as parallel with the boundary and it can be normal to boundary. If that's the case, then we will always have component that are always normal or parallel to the boundary. So parallel we call it tangential, and normal the orthogonal is normal. Okay, so we can actually split. Okay, we learn from vector is actually this E1 can consist of two different vector, right? Okay, which we have here is E1 tangential. Okay, of course with the vector, and you have E1 normal. Okay, which is normal to the surface. Okay, normal to the surface. And we have also for this one, we can split it to two equivalent. Okay, okay, so we have E to T, which is tangential, and we have E to N, which is normal to the surface. So with this, it is more simpler because we now going to have both normal at 90 degrees of normal to the surface, and also we have E to T for the tangential parallel to boundary condition. So now we don't need to worry like things that we cannot a bit cumbersome, which is, for example, the angle. Okay, so now we already make some standardization. So we have tangential component. Okay, sorry, I want to search for my, okay, this one. Okay, so at the boundary here, what we will have, okay, we will have tangential component, and we also have the normal component. Okay, so let's say we take, okay, we try to settle for n first. Okay, try settle for n first. Let's say what is your normal component? You have E1n. Okay, here, if electromagnetic wave in medium 1, and you also have E2n. Okay, which is our conductor, for example. And for the tangential, we have E1t and E2t. Okay, now we taking that at this boundary condition, we taking that boundary condition 1, we take as the normal component. Okay, and boundary condition 2 as the tangential component. Okay, before I further explain, you guys still need to refer to Sadiko book for more detail. Okay, I always remind about this because Sadiko book will have more details. Okay, and because logically I cannot cover all in the lecture, And also please watch the lecture video entitled supplementary, link as with the label as supplementary in at e-learning, and I believe most of you guys have done it. Thank you for that, because this will help you. Okay, the lecturer is experienced. He was my lecturer teaching EMT, associate prof. He already retired, so please watch it. For me, it's okay. You guys can learn from everyone as long as it can help you. I honestly, maybe my explanation is not clear, okay, and maybe I'm limited in explanation, okay, but it is logic because I'm new, okay. As time goes by, I will, inshallah, I will be as experienced as them, okay. But for now, please, to help yourself, watch their lecture, read Sadiku, do your tutorial, do your handout, okay, and expect, of course, challenging question from test and examination. That's why you need to always have practice, okay, to help you to familiarize. Okay, now without further ado, we settle for this one first. I divide this page, right, so that we can do some comparison, and it is easy for you guys to see. Okay, I put this as maybe 1 again, and 18 April, okay, week 5. Okay, okay. Now let's say we want to settle for this one first, the boundary condition one, okay, which is the normal component. Okay, I hope it's clear. No? Okay, let's say we have the same thing. We just copy the boundary. Okay. In this condition, we only focus on normal component. Okay, and if there is a tangential component, we try to ignore it, or we try to make assumption in such a way that this tangential component will be ignored. In this case, for this case as well, for boundary condition 2, which is the tangential component, the same thing. If there is a normal component exists inside here, we will try to make assumption so that it will be ignored. Okay, because we dedicated this is for normal, and this one is for tangential. Okay, now for normal, for example, okay, imagine this, and then you have a normal component here, which is your E to N. Okay, and this one is your E 1N. Okay, as your normal components. Okay, and imagine that we actually have some charges. Okay, some charges built up at the surface. Okay, it's assumption. So if it's not exist in the real time, I mean in the real situation, we can just substitute with equal to 0. Okay, so just imagine that we have some charges here, so that we can solve the equation using our electrostatic approach. Okay, so we need to make sure there is some charges. Okay, but we can omit it later on if it's 0. So let's say we have a rho s here. Okay, let's say we have flow charges, surface charge density. Okay, and then let's say we have this E2N normal and E1N normal. So we try to solve this in such a way that we will get the value of the E. Okay, we try to relate it with what we know. Okay, so let's say we have this, so this one direct to this. So what coordinate that you think is the most suitable to settle this? So is this a cylindrical? Okay, cylindrical. Okay, then you also learn that you know that if you use cylindrical, means we will have some in any coordinate we have some surface. Okay, Okay, so what surface we have? We have this surface, surface 1, and you have this as your surface 2, and you have the below part which is your surface 3. Okay, because now you can see that we have some surface, we have, so we try to solve from what we have known. Okay, here we can use Maxwell equation 1. Okay, if you guys forget what is Maxwell equation 1, you can go to the Gauss law page. Okay, Gauss law Maxwell equation, you see about this first Maxwell equation. So it stated that the divergence of D is equals to rho V. Okay, and of course if you want to have more detailed version, okay, and we know that actually our charge is equal to our charge enclosed for if we want to use Gaussian. Okay, so this is Gaussian, so you have to have a closed loop. Okay, then you have your D and dot with your ds. Okay, and then it's equal to Q enclosed. Okay, now we can see from here how many surface that we have. 1, 2, 3, right? So we will have 3 surfaces integral here, and that will equivalent to our dq. Okay, so take the first surface, which is here. You have your D is emanating out, sorry, D1n. Okay, D1n emanating out, and you see for the surface, okay, the normal surface, the normal to our surface is in the same direction as E1n, so it is positive, so it doesn't have any, they are in the same direction, so they are just like this. Okay, then the next one, sorry, I should maybe write in integral so that you guys more understand the step by step. Sorry for that. So for the surface 1, you have surface 1. Okay, then you have your ds 1. Okay, plus, how about surface 2, and you have ds2. Okay, which is due to the surface 2, and plus s3, which is on below part. Okay, ds3. Okay, and you see this is Q enclosed. Okay, Q enclosed, you see this is all about surface, right? So this one is can be your rho s ds. Okay, now continue again for what I just now I jumped, sorry for that. So ds, you can see it is D is emanating out, and your surface normal to the surface is also emanating out the same direction, so that's why we have D1n s. Okay, and then how about this one? Okay, this one, if you see, it is emanating out, emanating in parallel to the boundary. Okay, emanating in parallel to boundary, so this is actually the tangential component. So like I told you guys, we try to make some assumption so that it can be ignored. Okay, so in order to ignore this tangential, because we're going to have here instead of here, so we need to assume, we need to make some assumption that h is too small, that is approaching to 0, means negligible. So instead of this, which is we provide the tangential, which when we assume h equals 0, so this will be cancelled out. Okay, it's not inside, it's not considered anymore. And how about this one? Okay, you see D1 is in this direction. Okay, the D normal in this direction, you can see it's in this direction. and however our surface 3 is in opposite direction. Okay, so there should be some negative. Okay, there should be negative because this one is opposite as this D2N. Okay, so you will have D2N, okay, as, okay, you should know why this negative, right? Because they are opposite direction. Okay, and then here when you do the integral part, you know the rho s is constant, and this one you will have the surface. Okay, you have surface. So you can see that there is the same s, so you can cancel out them. So in the end you have d1n minus d2n equals to rho s. Okay, so this is your boundary condition number 1, which is the normal component. So let's say there is no charges. Okay, there is no charges, so we can replace this rho s with 0. Okay, so this one is, we assume also there is a charge just now, right? We assume there is a charge in order for us to solve this using our electrostatic approach. Okay, so now this is the normal. Okay, how about the tangential component then? Okay, tangential component, similarly we will ignore the normal part, okay, if there exists, so that we only consider tangential. Okay, so we try the same. We try to, okay, we do the boundary again. Okay, and this is of course your boundary 2, this is your boundary 1. Okay, now we have the tangential component. So this one you have E1t, sorry, we just try to, okay, E1t, and second you have E2t. Okay, so what is the related equation that involve this E that we have learned before? Okay, so you guys can look at Maxwell equation. Number 2, okay. What Maxwell equation number 2 says is that in the closed integral, okay, in the closed integral E along the DL, okay, it will have 0 value. Okay, so now we try to solve this situation of tangential component with this, using this equation. So logically this is a closed loop, so closed loop of DL, so we cannot have this, so we need to have a closed loop. Okay, so we make a loop from 1 to 2. Okay, you can see the direction. Okay, so we have from 1 to 2.2, 2.3, 2.4. Okay, from 1 to 2, 2 to 3, 3 to 4, and 4 go back to 1. Okay, so as similar as this, you also have the h. Okay, sorry, just now we assume h0 because sorry forget it, I forget to label. This is your h. Okay, but it's understand already. H is height. Okay, so h, then also of course this will be your length. Okay, okay, you now can see, right, this is your E2t, the direction. Okay, okay, now we try to expand this equation with respect to this condition. Okay, so first, closed integral, right? So this is from point 1 to point 2. You have E dl, okay, vector. Okay, and then from 2 to 3, and from 3 to 4, and from 4 to 1. Okay, so if you guys notice, this is your tangential, then you have this value here, so this is your normal. Okay, Similarly, like in the case of normal, we want to remove the tangential component. The same goes for tangential component. We will try to remove the we will try to remove the normal component. So how we do it? The same thing. We assume that h is approaching to 0, means it will be negligible. So this component 2 to 3 and 4 to 1 will be negligible. So this one will be negligible. Okay, we take out this as 0. So you end up with only this one. Okay, sorry. Goes to 0. Okay, then you try to solve it. Okay, try to solve it. So here is your E1t. Okay, remember this one times with this one, it will result in scalar. Okay, so just so you don't have direction anymore. So this one, then you have your length. Okay, how about this one? Okay, how about this one? E is in that direction. Sorry, E is in this direction. Okay, E in that direction, you see. However, your DL is from 3 to 4. Okay, your DL is from 3 to 4, which is opposite. Okay, at here. Okay, your DL is here, and your E to T is in the other direction. So they should be negative here to show they are in opposite direction. But the length is still the same. Okay. So taken out the L because they are the same. Okay, so you will have E1t equals to minus E2t equals to 0. Okay, then you can make some rearrangement. Then you have E2t. Okay, E1t equals to E2t. Okay, so here you can see the comparison, right? That's why I want to create a table, split the page into half. Okay, now we try. Okay, we have these conditions already, so let's make some comment on this, what we have gathered. Okay, okay, now I want to continue to make some generalization about this. So now we came across to conductor. Okay, based on what we have gathered here, conductor, free space, boundary. Okay, boundary condition. So what equation? We can just transfer here d1n minus d2n equals to rho s, and also we have, this is of course your boundary condition of 1. Okay, then boundary condition of 2, you have this equation. Okay, okay, remember, if you see this, it's already in scalar form. Okay, it's in scalar form because this is dot product and this is also dot products. Okay, I hope it's clear because I use the ring light. I hope it's clear. Let me change the lighting. Okay, sorry, I think this is the clearest that I think that. Okay, sorry for that. Okay, so here is your d2n, this one with respect to your conductor. Okay, and 1n is your free space. Okay, so 1 is your free space and 2 is your conductor, for example. Okay, conductor. So what we have learned in the electric and okay, let me go first. Okay, what we have learned in electric in static conditions, okay, is E equals to 0, right? Okay, so we will, this one, E is related to D, right? So your D2N, which is actually is related to your E, right? So if E is under static condition is 0, so this one D is also will be 0. Okay, so then you will come across the simpler form, which is D1N is equals to our rho S. Okay, and how about E1T and E2T? The same thing. You see this is 0, right? So this one will be 0. So you will come across that E1T is equals to E2T is equals to 0. Okay, well, the thing that I have covered before. Okay, so it is much simpler now. Okay, now you have this equation. Okay, for the conductor free space boundary condition. Okay, now let's say the real boundary condition, the real boundary doesn't have this flat surface. So you make it example like this as your boundary, right? Okay, and maybe this is your boundary 1 and this is your boundary 2. Okay, so when you have we'll make some orthogonal. So when you have this is your E2, this is your E1, right? Okay, now we want to see where is the normal. So the normal is here and the tangential is here, and for here the normal is here, the tangential is here. Okay, at this space it is at this point it is correct. And let's say if you have okay, let me do it more realistically. Okay, and then let me okay, so it's easy for me to draw it anyway, sorry for that. So now let's say we have here, then if you have your E2 here, okay, and then you have E1, for example, then you have your E1 here. Okay, then you try to draw first the normal line. Okay, the normal line is here. Okay, now you can see that if your E2N is different now, E2N is here. Okay, the normal component is here and the tangential component is here. Similarly, for this case is here for E1N, and for E2N, and for E1T is the different direction. Okay, you can see even though they are on the same boundary condition, but if we take this different point, it will result in different normal and different tangential. So in overall, you can see we have a lot of directions. Okay, okay, so for example, now if you have this D1N, okay, D1N and rho S. Okay, what is rho S? Rho S is valid if there is charges. So this is a surface charge. Okay, so imagine we have a positive charge along the way. Okay, if we have positive charge along the way, then if we take this, okay, for example, if we take this now, okay, I try to not to use the same drawing because it will be like complicated. Okay, so if we have this as our D normal, okay, because this D about D1 normal, and it's normal to this surface, so we have D, okay, D1N equals to rho S, right? But if we want to have some direction, because this is actually a vector, right? So you will have D1N normal and rho S, this is constant. Then we have a unit vector AN, which is normal. Okay, so this is how you write it. Okay, so I hope this is clear for you. Okay, and you guys can take a look. Okay, inshallah we will cover I will try to see what will be covered later on, okay, for week 5. We will cover, next we will cover about the dielectric under static condition and dielectric to dielectric boundary condition, and also capacitance for the application parts, okay. So thank you for this watching. See you soon.